as we just saw, higher order differential equation or a system of differential equations can be always converted to a system of first order differential equations with probably more unknowns, right? So if we have a third order differential equation, we introduce new variables that denote the first, the second, and the third order derivatives of the unknown functions and then we just convert the differential equation to a system. Well, if we have a system of higher order differential equations, we can always do the same trick. So my point being is that all that there is in the subject of differential equations is systems of first order differential equations. So it's always like that, because higher order equations or systems can always be converted to a first order systems of differential equations. And for instance, it means that our theorem of existence and uniqueness of solutions, since if you look at its proof, then essentially the proof is applied to systems of differential equations rather than to individual differential equations. So which means we already have the uniqueness and existence of solutions of initial value problems, not just for individual equations, but for systems of differential equations, and well, by the virtue of this argument, for higher order differential equations too. So there are some special types of systems. An autonomous system of the ordinary differential equations is a system of differential equations where the right hand side does not include the independent variable explicitly. So notice that here x is a vector function, so x here is actually Rn, belongs to Rn, but it is a vector function of a scalar argument. So then a linear system can be written like this, so where the right hand side is some matrix. So here you can think of x as an n by 1 vector x1 of t, x2 of t, and so on, xn of t. So this is n by 1. So its derivative is also an n by 1 vector, and then p of t is an n by n matrix, and g of t is an n by 1 vector. And so this is a linear system. Then a homogeneous linear system is where there is no constant term, there is no plus gt. And a linear system with constant coefficients, well, could be homogeneous or non-homogeneous, but in any case, the important thing is that here the matrix of coefficients is not is a constant matrix, as opposed to a non-constant matrix for a generic linear system. But notice that a linear system with constant coefficients, if it is non-homogeneous, then the plus gt is not supposed to be constant, right? So here is not constant, right? Even for systems with constant coefficients. So in other words, the word coefficients here refers to the matrix A rather than to this free term. So here is our examples. Nonlinear autonomous system is a system of well, it is nonlinear, it is autonomous because the t does not appear there, and it has 4 equations. So our first example with tanks was a linear autonomous non-homogeneous system with constant coefficients. So here the free term plus b is also constant, but it may not be so, generally speaking. So here is a linear homogeneous system, right, because we can rewrite it in this form. But here the coefficients are not non-constant, but there is no the term plus gt, so which makes it homogeneous. Okay, so now I suggest that you try to do this little revision quiz.